in the last period, in the last video, we have seen the definition of differentiation. Even we have seen some standard formulas to find out differentiation. First three formulas are to find out differentiation of algebraic function. If you observe the list of formulas, first formula is x raised to power n, second formula is 1 upon x raised to power n, and third formula is root x. Then we have seen 6 formulas to find out derivative of trigonometric function. Derivative of sin x, cos x, tan x, sec x, cot x, and cosec x. 2 formulas to find out derivative of exponential function, e raised to power x and a raised to power x. And 2 formulas to find out derivative of logarithmic function. One is log x and second formula is log x to the base a, and the last formula is derivative of constant function. All these formulas we have seen in the last video. And even we have seen 4 important rules. First rule is called as addition rule, second is subtraction rule, third is product rule, and fourth is quotient rule. Now we are starting first important article from class 12. So here we are finding differentiation, means derivative of what? Composite function. So first we will try to understand what is the meaning of composite function, and later on we will see how to find out differentiation of composite function. So here f is a function from set A on set B. So if f is a function from set A on set B, f is function from set A on set B, and g is a function from set B on set C, and g is a function from this set B on this set C. Again, observe the condition in the definition. This f is a function from set A on set B, and g is a function from set B on set C. Then the function from set A on set C is called as composite function. So now again see what we have written. Composite function is called as what? Function of a function. Now here we are denoting variable, say, by x. Generally we are denoting variable by x. So image of this x under the function f will be what? F of x. All this part we have seen in first video also. So image of x under the function f is denoted by f of x. Now try to understand. Image of what? F of x. Image of f of x under the function g will be denoted by what? G of f of x. Because we are finding image of what? F of x. Under the function g will be denoted by g of f of x. Now if you observe here, f is nothing but function of x. What is x? X is a variable. So f is a function of variable. But in this case, g is function of f of x. But f of x itself a function. That's why we can say that g is what? Function of a function. And such type of function of a function are called as composite function. That's why we can say that composite functions are also called as what? Function of a function. So function of a function means composite function, and here it is denoted, it is what? It is denoted by g of f of x. In short, it can be written as g of f. Means g of f is nothing but function from what? Set A on set C. So it is denoted by this notation, g of f or g of f of x. So g of f is nothing but a function from what? Set A on set C. So hope the idea about function of a function is clear. Again, we will try to understand this definition by considering one example also. So let us suppose that here one set is there. Let the element of this set be x. Image of this x under the function sin will be what? Sin x. Image of x under which function? Sin will be sin x. And image of this sin x under the function log will be what? Log of sin x. Log of sin x. If you will observe here, sin is a function of x, means sin is a function of variable, and log is a function of what? Sin x. Sin x itself a trigonometric function, and log is a function of this trigonometric function, means log is a function of function, and such function are called as what? Composite function. What is our standard formula? Derivative of log x. Such type of function, it is written in what? Standard form. Log is function of variable. But if this variable is replaced by some function, sin x is what? Function. If variable is replaced by some function, then we can say that this is the example of what? Composite function. Let us consider another example. Say tan tan instead of x, if I am writing here log x, means tan is a function of what? Logarithmic function, means it is function of function. Such functions are called as composite function. Let us consider e raised to power x instead of x. E raised to power x is what? Exponential function. But instead of x, if I am writing here sine and sine tan x, then it will become what? Function of a function of a function. Because sine is function of tan x, it is function of function, and exponential function is function of this function, means function of function of function. Such functions are called as what? Composite function. Again, let us consider another example. So let us consider here variable I am denoting by x. Let the image of x under the function log will be log x. Let the image of log x under the function sine will be what? Image of log x under the function sine will be sine log x, and image of sine log x under the function say tan will be what here? Tan of sine of log x. Means here what result we have got here? In log is sine is the function of log x and tan is the function of sine log x, means function of function of function, and such functions are called as what? Composite function, or we can say that it is combination of 2 or 3 functions. Such functions are composite function. To find out derivative of composite function, we are going to prove one theorem. That theorem is nothing but formula for us to find out derivative of composite function. So now let us try to prove the first theorem, which is also called a chain rule. So first we will observe the given condition and later on see how to prove it. This is nothing but one formula to find out derivative of composite function. So after the proof, we will see how to find out, how to apply this formula to find out derivative of composite function. Observe the given condition. Y is equals to f of u is the differentiable function of u. It is given to us that y is a function of u. Y is nothing but what? Function of u. It is given to us y is function of u. Okay. And this function is denoted by what? F. Y is nothing but function of u. And u is a function of x. U is nothing but what? Function of x. This u is function of x. And this function is denoted by what? G. So these are the given condition. Again observe here, y is nothing but what? Function of u. And second condition, u is what? Function of x. U is nothing but function of, and y is function of u. Now again, if you observe here very carefully, y is differentiable function of u. Already in the first video we have seen that y is differentiable function of u is denoted by what? Dy upon du. Y dy upon du. And u is differentiable function of x is denoted by what? U is differentiable function of x. It is denoted by du upon dx. Now, if the value of x changes, let the denote the change in the value of x by what? Delta x. Means I am denoting here increment in the value of x by delta x. As the value of x changes, value of u also changes. Let us denote the corresponding change in the value of u by delta u. If u changes, then y also changes because y is a function of u. Let us denote the change in the value of y by y plus delta y. Means here increment in the value of x we are denoting by delta x. Increment in the value of u we are denoting by delta u. In the same way, increment in the value of y we are denoting by what? Delta y. Now here if x changes, u also changes. If u changes, y also changes. Means what here? If one value changes, another changes, then third value also changes. Means this is nothing but one chain. And that's why this formula is called as what? Chain rule. Getting it? Now, according to definition of differentiation, if y is differentiable function of u, then which limit exists? Already this definition we have seen in the last video. So limit, if here du is there, then here delta u tends to 0 is there. Delta u tends to 0, delta y upon delta u. if this limit exists, we can say that function is differentiable. But here already it is given to us that function is differentiable, means y is differentiable function of u. Then we can say that limit exists. Limit exists means function is differentiable, or we can say that if function is differentiable means already this limit exists. In the same way, it is already given to us that u is differentiable function of x. And when we can say that u is differentiable function of x, means limit delta x tends to 0, delta u upon delta x. If this limit exists, at that time we can say that u is differentiable function of x. If this limit exists, we can say that u is differentiable function of x, and symbolically it will be denoted by this notation, du by dx. Now what we have to prove? If these are the given conditions, then we have to prove that y is differentiable function of x. Y is differentiable function of x. It is denoted by this notation, dy by dx. These are the given conditions. And this is nothing but we have to prove here. Getting it? So we have to prove that y is differentiable function of x. But when we can say that y is differentiable function of x, if this limit exists, means limit delta x. If dx is there, so then write down delta x tends to 0. In the numerator, if dy is there, then here we should have to get delta y, and in the denominator what? Delta x. If this limit exists, at that time only we can say that y is differentiable function of x. Now we have to prove that y is differentiable function of x. For that purpose, we should have to prove that this limit exists. Is it clear? So let us make the use of this given condition to prove that y is differentiable function of x, y is differentiable function of x, and it is given by this formula. Okay. So now first we will suppose that let x changes to x plus delta x, where delta x is nothing but increment in the value of x. Already we have shown in this, whatever may be the changes, increment, we have already shown in this figure. In examination, not necessary to draw this figure, just for your understanding we have drawn this figure here. So here what we are supposing, let x changes to x plus delta x. If the value of x changes, then u also changes. Correspondingly, u changes to u plus delta u, and if u changes, y also changes, and y changes to y plus delta y. So where this delta x, this delta u and delta y are nothing but what? Are small increment in x, u and y respectively. These are nothing but small increment in the value of delta x is the increment in the value of x, delta u is in the increment in the value of u. In the same way, delta y is the increment in the value of y. Already we have shown it in the figure also. So hope these ideas are clear to you. Now we are using given condition. What is the given condition? These are the given condition, and this is the result which we have to prove. Now according to given condition, here delta u tends to 0 is there, but in our required result we will require delta x tends to 0. Now we will try to show that as delta x tends to 0, delta u also tends to 0. So as delta x tends to 0, let us see what result we will get. As delta x tends to 0, delta u can be written as delta u divided by delta x. Since I am dividing by delta x, that's why I am multiplying by delta x here, is equals to. Now observe the given condition. Value of delta u upon delta x as delta x tends to 0. What is the value of delta u upon delta x as delta x tends to 0 will be equals to what? Du upon dx. This is the given condition. Already we have written here the given condition. So value of delta u upon delta x as delta x tends to 0 will become what? Du upon dx. And this delta x and this remaining delta x tends to 0. So replace it by 0, and 0 into any number will be equals to 0. So what result we have got here? So therefore, as delta x tends to 0, as this delta x tends to 0, delta u also tends to what? 0. Delta u also tends to 0. Let us denote this result say by equation number first. Later on we have to use this result. Now what we have to prove here? We have to show that dy upon dx is equals to dy upon du into du upon dx. Now we are taking randomly we are taking one step here. So try to understand it. Observing our required result, we are taking one step. So now on the left hand side dy upon dx is there, that's why we are taking delta y upon delta x is equals to, in the numerator keep this delta y as it is and in the denominator keep this delta x as it is. Now simply I am multiplying by delta u, that's why I am dividing by delta u. In every theorem we are taking such type of steps, just observing our required result. Now simplifying it, we will simplifying it and using the given condition we are going to prove this result. Now we are taking limits on both sides. So taking limit as delta x tends to 0 on both sides. Okay. So taking limit on this side, limit delta x tends to 0, delta y upon delta x. We have taken limit on left hand side. In the same way take the limit on right hand side also. Limit delta x tends to 0, delta y upon delta u into delta u upon delta x. Just simply we have taken limit as delta x tends to 0 on both sides. Now take the separate limit of both the terms. Keep the left hand side as it is. What is left hand side? Limit delta x tends to 0, delta y upon delta x, keep it as it is. Now take separate limit of both the terms. So take the limit of first term, limit delta x tends to 0, delta y upon delta u into limit delta x tends to 0, delta u upon delta x. Simply we have taken separate limit of both the terms. Now again if you observe here very carefully, so here this limit delta y upon delta u, keep it as it is. Keep this next term also as it is, limit delta x tends to 0, delta u upon delta x. Okay. Now we are replacing this delta x tends to 0. We are replacing delta x tends to 0 by delta u tends to 0 from equation number first, which already we have proved here. So replace this delta x tends to 0 by delta u tends to 0 and keep this left hand side as it is, limit delta x tends to 0, delta y upon delta x. Okay. Denote this new equation say by equation number 2. Now observe the given conditions very carefully. Already we have discussed on it. So what is first condition? Y is differentiable function of u. So already we have seen that if y is differentiable function of u, then it is denoted by this notation. If this differentiation exists, means which limit exists? Limit delta u tends to 0, delta y upon delta u. This limit exists is given condition. What is the second given condition? U is differentiable function of x. U is differentiable function of x is denoted by du upon dx. If this limit exists, if this differentiation exists, means which limit exists? Limit delta x tends to 0, delta u upon delta x. Now if you observe, these are the given conditions. Okay. The better way, write down these given conditions. Since y is differentiable function of u and u is differentiable function. Differentiable function of x. If y is differentiable function of u, then just now we have discussed it is denoted by dy upon du. If y is differentiable function of u, means which limit exists? Limit delta u tends to 0. Limit delta u tends to 0, delta y upon delta u. This result we have got using definition of differentiation. And second given condition, u is differentiable function of x. If u is differentiable function of x, then it is denoted by du upon dx. And just now we have seen that if this function is differentiable, then which limit exists? Limit delta x tends to 0, delta u upon delta x. Now, if you will observe here, limit delta x is there, but in our according to this first given condition, sorry, here limit delta u is there. But here we have got what? When delta y upon delta u is there, what is our required term according to given condition? Delta u should be there. But here what we have got? Delta x. That's why already in equation number first we have proved that as delta x tends to 0, delta u tends to 0. अगर हम यहाँ पे delta x रखते हैं, then we are not able to apply what? Given condition. To apply this given condition instead of delta x, what we will require? Delta u. That's why already we have shown here as delta x tends to 0, delta u also tends to 0. Now, if you observe these two limits, check whether same limits are there on the right hand side of equation number 2. Check that. First limit. Is it the first limit? Yes, the same limit is there on the right hand side. If you observe the same second limit is the same one here. According to given condition, these two limit exist, means we can say that these two limit exist. So now we are able to say that both the limits on which side? Right hand side of equation 2 exist. So here we are able to write down, therefore both limits on right hand side of equation 2 exist. So if both the limit exists means what? We are getting one real number which is the limit of that function. Suppose that for simplicity, suppose that limit of first function is say 5 and limit of the second function is say 6. This is our supposition. So what multiplication we are getting here? 5, 6 are 30. Means if we are supposing that this value is 5 and this value is 6, then 5 into 6 will be 30. 30 will be the value of this limit. Means if both the limit exists, at that time only we can say that limit on right hand side exists. If we are supposing that this is 5 and this is 6, 5 into 6 will be 30. Means 30 will be the value of this limit. Means if these two limit exist, at that time only we can say that this limit also what? Exists. So already we have written both the limit on right hand side exists, and on this limit on left hand side is depend. So since both the limit exist, that's why we can say that this limit on right hand side also exists. So here therefore we can say that therefore limit on left hand side of equation 2 exists. Hope you have got it. So this limit on left hand side depends on what? Both these limit. But according to given condition, both these limit exist. If this limit exists, means we can say that this limit is also exists. And our definition of differentiation says that if this limit exists, then it will be denoted by, observe here, delta y upon delta x as delta x tends to 0. If such limit exists, then it will be denoted by what? Dy by dx. So therefore limit on left hand side also exists and is denoted by, it is denoted by what? Dy upon dx. It is denoted by dy upon dx. Now observe the result what we have got here. Now all these values we are substituting in equation number second. So this limit is denoted by dy upon dx. So therefore equation second becomes, so what equation second becomes? This value we are denoting by dy by dx is equals to, this limit we are denoting by what? Dy upon du. Dy upon du into, and this limit we are denoting by du upon dx. So this limit is this one and will be denoted by du upon dx. And this is the result which we have to prove here, and this result is called as what? Chain rule. And this rule is applicable to find out differentiation of composite function, where composite functions are called as what? Function of a function. Applying this theorem, we are going to prove again some standard formulas to find out derivative of composite function.